Hi, I'm Peter Geoghegan, Postgres major contributor and committer. I work on areas such as B-tree indexing and vacuuming. This includes work in Postgres 14 and 15, some of which I'll be talking about today. I work for Neon, a startup that is creating a version of Postgres with disaggregated storage optimized for the cloud. My colleague Heikki Linnakagis is talking on this subject at the same conference, so you might want to check that out. Thinking about the logical database. If you want to review my citations, if you have that interest, you can download my slide deck by following the URL you see at the bottom of the screen now. The citations are workable hyperlinks, so I've made that easy for you if you want to really get into the weeds with it even more, if you have that inclination. So that's something that I sort of want to enable by doing this talk. This is kind of just a starting point. It's not real. It's not. There's no end point in this talk. So now, first of all, some basic definitions. I want to define the logical and physical database as best I can, and these terms really come from the concept of physical data independence. So we'll start there. The term physical data independence rose to prominence in the 1970s. At that time, certainly in the early 70s, the dominant paradigm were things like hierarchical databases or network databases. These were characterized by great inflexibility in terms of schema, where the user had to pretty explicitly specify the schema in a way that anticipated the access patterns. In contrast, of course, relational systems work, they have theoretical underpinnings from set theory. They operate against relations with tuples that have no particular physical ordering. So the idea of physical data independence, if you were going from a system like IMS to one of the early relational systems, would have been quite clear. It wouldn't have been something that was the source of any confusion because it was such a sea change. These days, though, while there are still, I would say, meaningful gradations of physical data independence, it's harder to pin it down because these are relatively fine shades, certainly compared to the situation in the 70s. I still think it's worth trying to do that, though. These concepts do seem relevant and important to us, in particular as people who are working on storage internals, indexing, concurrency control, that sort of thing. So here's an example of what the logical database might mean. It is just an example, though. This is taken from a paper from the early 1990s, which is a modeling study of the TPCC benchmark, the then very new TPCC benchmark. So it's presenting something which is akin to, although not quite, a schema for an application. TPCC is a sort of simulated network of warehouses and with customers, with distributors. So it's sort of presenting the business side of it alongside some decidedly physical aspects. You see there tuple length. So that's obviously not entirely logical. What's especially not entirely logical is the way that they present this information alongside the number of tuples that would fit on a 4K page. And if you look at the detail of that, you'll see they're ignoring tuple overhead as well as page overhead. So that number assumes that there's no overhead for storing tuples at all, or for that matter, for putting them on a page, which is not really realistic. But this really needs to be interpreted in the context of the whole paper. It's not something, and that may be always true with something in the same general category. The details are going to vary. The essential part is the idea of modeling the relationship between useful work and physical costs, such as physical IOs. That's maybe the essential part. So in the case of this paper, they're looking at TPCC, which is by its nature very IO bound. It doesn't really exercise concurrency control. Arguably it should, but it doesn't. And so it makes sense to reduce it to a buffer hit rate, at least in respect of the IO costs, and to emphasize that over other things. This is also useful because TPCC is intrinsically a database benchmark that can be scaled linearly or near linearly. In fact, you kind of have to in a way, because there are rules about the number of transactions per minute per warehouse being how you define the size of the database. So it is intrinsically something that has to be able to scale up and down. And so having this model of the costs and benefits that's sort of directionally accurate as a starting point is potentially quite useful. If you were able to relate a buffer access hit rate in your actual real world system to their model, then it ought to follow that you can generalize from that. You ought to be able to predict ahead of time what the buffer hit rate will be with a much larger database. If you were to find that your prediction was wrong, or only became wrong at a certain inflection point, that would be interesting information. That would be something that would presumably be worth investigating. So having this model that's sort of directionally true, I think, could be quite useful. It seems to me to be related to the way that we use sometimes concepts such as read and write amplification. These are concepts that come from the world of flash storage. If you're somebody that's creating a flash translation layer, then quite naturally you are you think about useful work purely in terms of bytes written and bytes read. You don't get involved with the requirements beyond that. There's no difference to you between one byte or another. Whereas if we're to repurpose concepts like that when discussing the design of a system like Postgres, I think it's necessary to have some notion of base unit of useful work in order that we can sensibly talk about what it is we're actually amplifying. Because, I mean, by definition, we're writing the data several times, if we're lucky, only several times. So there needs to be some way in which it's grounded in physical, practical reality. It's nuanced. The only fundamental aspect of this physical logical database thing is the idea that there is independence, and that's a good thing. The idea that we want to be very careful about not over specifying what it is that we require from the representation of the data, that it be flexible, that we have various means of optimizing the system with that in mind. So there's a tension there. What I'm really examining in this talk is how that tension works, how in detail to think about how the logical database relates to the physical database in a variety of contexts, principally as a way of discussing performance enhancements or efficiency enhancements in Postgres itself, in access method code and things like that. I now want to turn my attention to the topic of two-phase locking and how it relates to version storage. I'm calling this a cultural divide. I think that's what it amounts to. This is a quote from a major reference paper from Hellerstein et al. About database systems in general. It's introducing what it terms transactional storage, or a transactional storage manager. First thing to note here, I think, the first thing that I find interesting is the idea of transactional storage. Notably, this is not storage used by a transactional database, it's transactional storage. That's how the abstraction is structured. It is quite directly the storage that is transactional. Transactional semantics are not emergent, they are directly embodied by storage. Second thing of interest to me is the fact that first in the list of 4 deeply intertwined components is a lock manager for concurrency control. This might be a little surprising to some people, at least, because in many ways concurrency control is very high level. If we look at how the SQL standard formalizes how concurrency control is required to work, it describes things like phantom anomalies. The lock manager for concurrency control stuff is very much concerned with these sorts of anomalies, and yet it's deeply intertwined with what would seem to be, anyway, things that are intrinsically about data structures. So, as a Postgres person in particular, that might be considered a little surprising. We have the luxury, in some ways, of not having to deal with this, certainly not in index access methods. We have a kind of a pure snapshot isolation. We version logical rows, in contrast with two-phase locking systems that don't exactly do the same thing. There's a kind of implicit knowledge here which is important often. To us as Postgres hackers, we have no difficulty understanding physical data independence as the utmost separation from the utmost separation from physical and logical database comes quite naturally. That isn't universally the case, though. The cultural divide, as I put it, between us and between people sort of versed in two-phase locking concepts is that they really don't have it so easy. And that's what I want to talk about now. Side note, I'm going to bucket systems in terms of two-phase locking or version storage. Postgres is sort of version storage snapshot isolation system here, and most of the major that also includes a storage engine from Facebook for MySQL called RocksDB. We'll hear more about that in a moment. But pretty much all the major old guard vendors I'm putting in the two-phase locking bucket. The real dividing line here may be their use of physical surrogates, meaning things like next key locking. Even when we use multi-versioning in a system like InnoDB or SQL Server, we see that the consequences of two-phase locking, excess locking that isn't sufficiently granular, becomes apparent. So what it seems to boil down to is these systems are really versioning objects rather than versioning rows. Physical surrogates refers to things that are representations of concepts from the application semantics point of view, or the logical database, that are directly embodied by physical things, such as, for example, a physical index tuple and a gap between that and its immediate neighbor that would represent a locked range. So it's an embodiment of a logical idea that's implemented in a very physical way, so to speak. This book, Transactional Information Systems, hints at the same. By this book is notably very theory heavy. A lot of stuff about concurrency control, serializability theory. Things like allowable transaction schedules are discussed in precise detail. However, it tacitly assumes two-phase locking with undo. This is even true in how it handles MVCC in one chapter. It makes quite clear why this is. The motivation is to make sure that all of that serializability theory stuff continues to apply. They quite clearly state they are assuming a single versioned database, even with multi-versioning. So it has nothing to do with an approach to garbage collection or vacuuming or anything like that. It's entirely about the basic soundness of these of the serializability theory. That is the clear motivation. So that's really the history. That's why these systems work in the way that they do. So to summarize a little of what I've said so far, with a two-phase locking system, there's implicitly minimal divergence between logical and physical database. It's hard to tell the difference. This is mostly due to concurrency control, and in particular the need to undo most, although not all, physical modifications. Whereas in Postgres, we have a high degree of flexibility. It's less monolithic, more decoupled. This is an enabler of extensibility, of course, and in particular extensible indexing. So it comes naturally to us. We can't imagine what it must be like. I'm trying to paint a picture of that. Something about MyRocks, which I'd mentioned is in the same category as Postgres. This is taken a quote from a paper from 2020 where some Facebook engineers explain many details of their migration to MyRocks and the motivation and the challenges and so on. MyRocks, as they plainly state, has a similar approach to concurrency control to Postgres. The starting point was InnoDB's next key locking. What they found, though, it was just much easier, having changed the storage of the system utterly for a variety of reasons to an LSM, which lowers write amplification. They then found that they couldn't really preserve next key locking from InnoDB. They had certainly some incentive to want to do so. The paper goes on to say that it did cause them considerable problems in production, but they persevered, presumably because they just didn't see an alternative, or at the very least it was very difficult to see one. The interesting part here, to me at least, is we can't consider anything in isolation here. We don't really have the luxury, and that seems to be broadly true. A brief side on MyRocks while I'm talking about it. I find interesting that MyRocks is like Postgres in a few other ways, even though the details, the motivation is very different. It uses compaction as an LSM-based system. So it's a totally transactional database system or storage engine that builds a transactional database system. On an LSM, it has compactions that are like vacuum. It has, by necessity, a lot of independence because, like, the sort of, there's no fixed relationship between the logical and physical as well. There's no use of logical surrogates, it would seem. And so I suspect for that reason they didn't have much difficulty in solving a long-standing problem in InnoDB, namely a problem with long-running transactions and how that would affect the, in particular, the performance of the long-running transaction. It would apparently be necessary for InnoDB to reconstruct pages at a historical point, which was very expensive. They were able to fix that problem. It turns out, even though I think they didn't really set out to fix that problem, they were able to, I think just because it's so much easier with versioning of rows, and considering that they had set out to do that anyway, really, It might not have been terribly difficult to solve this long-standing problem in InnoDB in passing, having done everything else. I'm speculating, of course. I can't prove this. I suspect it to be the case, though. It stands to reason that there's at least some truth to that. Here we see an image from a paper from Geoghegan, Modern B-tree Techniques, although similar tables appear in many of the same author's papers. This is discussing what for many people is a very confusing point, locks versus latches. This means the use of locks and latches is it's sort of specified here why one might want to use one or the other. You would think this wouldn't be complicated at all. And in one way it isn't. I don't think there's any difficulty in understanding the fact that a lock, which refers to a heavyweight lock, very much of the kind Postgres would use for certain things, has certain properties like deadlock detection, whereas in contrast, a latch, which refers to what we would call an LW lock or perhaps a buffer lock, isn't like that. It doesn't have deadlock detection. It's a reader-writer lock. It's sort of a low-level primitive akin to what you might use in an operating system kernel or something like that. So that basic definition is not the hard part, clearly, but what is difficult and tricky is to impose some kind of order on when one might use one or the other. This is the interesting part for me. So because of this use of undo and physical surrogates, you sort of need to think of things that are use locking as being those things that might require undo, which is very close to a thing that might not be like that. So for example, when systems based on two-phase locking require a page split, generally speaking, they need to have a dedicated autonomous transaction. They sometimes call this a system transaction. Other times it's called a nested top action. There are different terms that seem to be basically the same, refer to the same thing. These need to run and perform the required page split in order that so they do that synchronously in order that a transaction can insert onto the page if there's not space for the incoming item it wants to insert on the page. So there's a question then, or there would be a question about what do you do when you roll back the transaction, because for various reasons it's hard to undo a page split. It's a very intricate structure with concurrent access, that is B-tree pages are. So it's hard to undo a page split, and you generally speaking don't want to undo it. You just want to undo the logical modification, not the physical modification. So by having this system transaction, it's committed implicitly and immediately. You won't be rolling back the system transaction, you'll just be rolling back your transactions modifications. So that explicit division is a practical necessity. So you've almost done something physical that isn't physical. You've defined things in a way that might seem a little contrived to us, at least, in order that all of these concurrency control protocols can actually work in the general case. So if you get down in the weeds with it, you begin to understand how a person with this background might just find the distinction quite confusing. In Postgres, we use optimization in B-tree code for page splits, where we insert the new item onto the page that is split in passing. So rather than having a system transaction with its own mal record just for the split, everything is combined into one. There's no need to think in those terms, and we don't. This has obvious benefits here. Only having one mal record rather than two is clearly useful, and this kind of thing is second nature to us. We don't ever think to question it even. We take it for granted. And just as people with backgrounds in two-phase locking take other things for granted that we would find confusing and surprising. Here's another paper from Geoghegan. This one, options in physical database design. talks about the very same topic of the division between the logical and physical databases, although his explanation is more orientated towards the two-phase locking audience, that of course being the majority by far of people that will be reading such material, particularly at that time. This is from 1993. He also very clearly says that all of these things are interrelated and deeply intertwined, and it's confusing. And I want to be very clear, it is confusing. I'm in my let's say, in my hubris, I'm trying to explain something that's intrinsically confusing, as if my talks are not usually confusing enough. And I'm finding that it might be worth it in order to get the point across. I'm taking a little bit of a risk here, so I appreciate you bearing with me on this. So anyway, a lot of the stuff from this paper talks about things that really seem to anticipate some of what we have to deal with. Things like he calls them structural updates, which are really like non-hot updates. And he makes the point, they make things like bitmap scans easier, but there's other downsides too. It really is confusing. And if you take only one thing away from this talk, take away that point. Yeah, it's really confusing, and you should assume that you're going to have a very hard time of it if you try to just consider concurrency control in isolation when you're really sort of pursuing sea change, fundamental improvement sort of stuff. I think like you kind of have to accept the ways in which these things are likely to be interdependent and tricky and difficult. Systems that are based on two-phase locking that happen to use a heap for their table, such as, for example, DB2 or Oracle, perform free space management in using an approach that is transactional in every detail. This is the example that really makes the point to me. So everything is by necessity intertwined. There's a sense in which the distinction between physical and logical, conceptual implementation is very blurred. So you have to consider all kinds of eventualities. If you've got fine-grained locking at page level, what if you run into a situation where you don't have sufficient space to be able to roll back a transaction because of some subtle set of circumstances altogether at the same time? That would be disastrous. If a transaction that needs to roll back cannot roll back because there's insufficient physical space available, you've got a big problem. You've got a very nasty bug, and a subtle one too. So there's no sort of a la carte approach here, it would seem. You kind of have to buy into the idea that, in turn, the data structure that manages free space is itself transactional. It itself requires logical undo. We need to use heavyweight locking in many cases with these structures. Things are like this because if they weren't, then we'd have these rollback hazards. So we just don't have any. They don't seem to have any choice in the matter. This is a quote from a paper, same author, or one of the same authors as the Ares paper, or papers I should say. It's describing an earlier design that they're improving upon here in the paper. So what they run into is a situation where space isn't space. It's something that nominally belongs to a given transaction, at least within a certain scope. So there's kind of a sense in which free space is subjective and belongs to particular transactions out of necessity. Who can quite say where the boundaries between logical and physical lie here? It's really not simple at all. Okay. I want to talk now about a feature added to PostgreSQL 14, bottom-up index deletion. This is a performance optimization added to the standard B-tree index access method. It very specifically targets workloads that suffer problems from non-hot updates that cannot use the hot optimization, and as a result require a new round of index tuples for versioning purposes only, or at least for version purposes only in respect of those indexes that were not changed by the update statement, logically unchanged indexes, that is. It might be that one or two columns have been updated, which necessitates a round of versions for each and every index, not just those that were modified by the statement, if you like. So this is a very particular scenario that we're targeting, although an important one. We're targeting version duplicates. We're limiting ourselves to those indexes that were not logically modified. So quite naturally, the incoming item is bound to be a duplicate close by to the original so-called updated index tuple. Of course, you're not literally updating the index tuple, you're adding a successor version. So we only even consider this optimization when very specific conditions are met, namely, we know that there's a non-hot update and we know the index in question is one of those that was not logically modified by the update statement. So a lot of semantic information here is being handed down to very low-level code. This is something that can be very, very effective. It makes non-hot updaters, in a certain sense, clean up their own mess, often managing to prevent all version churn page splits, where before there was way too many. The index might increase in size by 2x, 3x or more in truly extreme cases. So that is obviously very useful if you happen to be affected by that particular pathological case in prior versions of Postgres. It doesn't really change very much about invariance, what it means for there to be a hot update or a hot chain or something like that. So it's just really changing the means by which we perform deletions in B-tree pages. We've long had a mechanism that's mechanically very similar, but is driven by completely different information. Same WAL record even, but totally different conceptual model. The picture you see here is of a realistic Postgres B-tree, much like the one you'd see on a primary key identity column, your standard sort of serial primary key, which would be the kind used in, say, the PG bench indexes. They're all one column, looks very much like this. The dimensions are what you see here. Now, typically the indexes would be much larger, but individual leaf pages would nevertheless look very much like what you see here in every detail. So what do we actually see here? Well, we see, since this is a unique index, we see that, and on a discrete type integer, we see that we have, in a certain sense, a lot of free space just with the standard index fill factor setting. We've got room for an extra 40 versions, if you like. Moreover, we know that we cannot, in this particular instance, anyway, have inserts onto this page because it's constrained. There's no, if you think about it in terms of logical rows rather than in terms of versions, and realize that this is a unique index, it follows, of course, that absent deletions at least, there's bound to never ever be any inserted tuples onto this particular leaf page. Any chance that if the page were to split, it would likely be, or almost certainly be, because of a sort of version churn page split. The specifics of this workload, of this scenario, are such that follows. The idea really comes from looking at things like this, variants of standard PG bench workload that were tweaked to have non-hot updates in various different ways, and realizing when looking at a particular leaf page where there was skew and therefore a disproportionate risk of one of these version churn page splits, I realized that quite simply we can easily prevent one of these from happening. They don't happen very often. When they do happen anyway, it could be minutes, even in extreme cases, before you see one. So it's actually, at least starting with this constrained case, not terribly difficult to, if we intervene in the right way in the right time, right at the last moment, to consistently over time avoid having even one of these version churn page splits. Our task is made easier by the fact that there really aren't that many heap pages pointed to by these particular leaf pages anyway. So really, it isn't that difficult to have some general notion of what's going on sufficient to intervene in just the way that's required. This is true even though we cannot immediately know just from looking at the page whether or not these are versions. We're applying low-level and high-level information together. And moreover, we're applying information that sort of belongs traditionally to the heap AM with information that is traditionally confined to the B-tree index AM. So the big important point here is perhaps the way that we're combining disparate information in order to make decisions as part of this whole process in order to prevent these version churn page splits, these pathological page splits that can have a very, very high cost if in cases where they are allowed to get out of hand. So it works in a variety of contexts, and not just in the context of indexes like the one I just showed you. I think for a bunch of different reasons. I would probably summarize it by just saying that it's focusing on not so much deleting index tuples that are garbage on a once-off basis, but rather conceptually it's a continual problem on, say, one particular leaf page. There's a tendency for growth in the number of garbage tuples to occur over time. The tendency is towards concentration. If you think about the problem that way, it's somewhat easier to solve the problem because we can reasonably expect again and again the same basic set of heuristics, which are primarily driven by the observation that there are certain duplicates on the page. The heuristics can work reasonably well because they'll tend to fall into a pattern of systematically being applied again and again. In cases where the optimization doesn't apply, it'll tend to fail very quickly and without too much fuss. Sometimes you kind of do want a version churn page split. In fact, like if there's an awful lot of contention on a very small index perhaps, then you maybe do want to have one or two page splits for those pages where there's actually a lot of contention that will, if you like, relieve the pressure on those pages. But you certainly wouldn't want 4 or 5 or 6 page splits, bearing in mind if every page splits once the index size doubles, and so there's kind of a way in which it naturally discovers the right sort of set of characteristics for a given workload in a sort of natural way, hence bottom up. In short, it keeps the physical database in sync with the logical database. It sort of has an imaginary ideal of the logical database and seeks to prevent the physical page from becoming excessively diverging from that ideal. In particular, having too many versions for any one logical row, at least with this particular scenario characterized by indexes that are not logically modified, it will certainly do that. So it's important not to miss simple things. It's easy to, though, because everything is so complicated. If they span multiple levels of abstraction to some degree, it's quite understandable in a way that it could be missed. So it's kind of in one way it's quite obvious, really, that something like this might work, but like actually exploring that possibility was something that took a long time. We saw earlier how for people versed in two-phase locking, the distinction between locks and latches, or indeed between logical and physical database, is intrinsically very confusing, in contrast with Postgres hackers who find the idea that it ever could be confusing, but otherwise don't find it confusing at all. So it's incredibly obvious to us, incredibly subtle to them. This is not a small difference. Let's not fail to appreciate how big a difference that is. A question I wonder, why wouldn't it work both ways? Why wouldn't there be something like that worked the other way around? Now, this is no small thing to figure out, because if that was true, it would probably be implicit. Implicit knowledge is important here. I couldn't expect, for example, to just read a paper and see a clear benefit that I could extrapolate from. It would be perhaps, as it is for them, lack of understanding of the implicit. It might be for us in the other way, the other direction. I've sort of proposed this division between two-phase locking and multi-version storage, but of course it is a little loose and artificial, which is good. As it turns out, we can, I think, expect to learn some kind of wisdom from some of the designs they've had if we go about it the right way. So we're not adopting the designs, but rather not failing to appreciate some subtle, perhaps, advantage that they have that we can attain in some other ultimately equivalent way. I have a few examples of this. First is free space management. So I've seen in Postgres there's a tendency for, there's no sense of ownership of pages. It's good that we don't have those rollback hazards that you'd have in a two-phase locking based system. Use a heap, but there's something to the idea, surely, that of sort of weak ownership semantics, being sensitive to the idea that this transaction or perhaps backend owns this heap page with some caveats, but that is essentially what we set out to do, at least. We want there to be no sort of... we want systematically to use free space in a way that has affinity with logical concepts such as transaction ID or even backend. There's also something interesting to the idea of transaction rollback, which is kind of in quotes, or should be. It's not tied to concurrency control, or it doesn't have to be if we go about it. I mean, again, rollback is primarily about concurrency control. It's not about garbage collection. An interesting question occurs to me about this. A question you might ask of somebody working on two-phase locking system. Why wouldn't you seek to optimize the case where you have to abort a transaction and wait synchronously? The client has to actually wait for rollback to occur. Why wouldn't you just hand that work off to a daemon process, which can, it can receive the same locks and finish the process on behalf of the client and allow the client to go and continue without having to wait? Why the necessity to wait? I believe the answer is, if you were to implement such an optimization, there'd be deadlock hazards, because presumably most of the time the connection would retry, and in so doing would deadlock with this daemon process. In fact, it could even be sort of deadlocking again and again, effectively live locking in a way that would never resolve itself. So there is some intrinsic logic to the idea of waiting and requiring the transaction, connection, whatever, to clean up its own mess. Recall how with bottom-up index deletion, we were sort of making the non-hot updaters on the hook for cleaning up their own mess. We don't want to allow sort of free riders, if you will. We don't want to allow these perhaps minority of transactions to make life hard for the system as a whole. They ought to be on the hook. That way, if they can never go too far with causing problems for the system. The system will tend to be much less likely to fall off the rails, just as a consequence of who is responsible for cleaning up the mess. And I think maybe transaction rollback, without anyone ever sort of thinking to acknowledge it, might have that quality to it as well. So there's something maybe to that. So maybe we could think about introducing a limited form of, we'll say, transaction rollback, not based on undo, but based on some kind of local cache of modifications to pages that would only apply to small transactions. In OLTP apps, of course, every transaction, or almost every transaction, is small. And I think this is quite important because it allows us to leave behind pristine heap pages where we wouldn't otherwise. We have to consider second order effects. We know for sure, because of the first order effect, that, or almost we know for sure, that the pages that we've dirtied will still be dirty at this juncture. So quite obviously we have every chance of avoiding a second dirtying of the same pages later on by being proactive about it. But then it's much more than that even, because we also have to consider the fact that if we don't do this, at some point somebody will be reusing that space, but it'll be for wholly unrelated logical rows. So we've missed the opportunity to start with a clean slate. When early in the lifetime of a heap page ought to be some kind of special, it ought to be a time when we sort of decide, okay, principally it's going to be, until we hear otherwise, principally it's going to be these transactions that will insert onto this particular heap page. And like making sure that we start with a clean slate really is just as important even as problems that happen later on when somebody updates or deletes. One more is related to the other two really. We have problems with freezing. There's lots of proposals on the table to deal with that, such as 64-bit transaction IDs. My observation on this in passing would be we don't have sufficient care about making sure that the data is in the first place organized according to certain rules. It might be useful as some much larger project dealing with these issues to make sure that the heap pages themselves start out with certain known information about which transaction IDs have modified those pages. We might have invariants. So essentially we would make the storage manager perhaps and the free space map and parts of the heap AM, the stuff that's in hio.c perhaps, would have a sense of this kind of thing. So we would reliably, or we would reliably follow certain rules about not mixing old with new, and we could even have certainty that that would apply as a hard rule, which we could exploit within vacuum. So again, taking the context, not seeing spaces being equivalent to any other space in any other heap page, understanding that there is a bigger picture, and understanding that semantics of the logical database do indeed matter, and indeed using that context in ways that heretofore might be considered unusual or considered something of somewhat of a modularity violation. I think it's worth taking the idea seriously that we really are missing the full context in places like the free space map, in places like the storage manager. In conclusion, a lot of these design decisions are interdependent. It's a very, very tricky business to know where to draw the line. As I've said already, there's a tendency that to really not know exactly where the line should be drawn. So I thank you for getting this far and putting up with the kind of hand wavy nature of this talk. That was a deliberate decision on my part to do the talk knowing full well that it would have that less than ideal quality. And I just think in general it's worth understanding how the other side thinks about it, if only so you have another thing to draw upon as a practitioner, as a person who's trying to enhance these things, trying to do better. So I will